In the case of a discrete probability distribution, the formula for the expected value is x as p of x. So we can just make a new column here, which is x times p of x. We get 0.1, 0.4, 1.2, 0.4, and 1. And if we add all these numbers together, we'll get the mean as 3.1. In the previous question, we found that the mean for this distribution was 3.1. We'll be applying the standard formula for the standard distribution here, which is I'm just going to write out the first couple of expressions to help you understand how this is calculated. So for x of 0, we have 0 minus 3.1 times the probability of x of 0, which is 0, plus for x of 1, 1 minus 3.1 times the probability of getting x of 1, which is 0.1, and so on. We'll have corresponding terms for 2, 3, 4, and 5. And if we do the math, the answer comes out to be 1.22. We are given a normal distribution with a mean of 1 gram per centimeter squared and a standard deviation of 0.1 gram per centimeter squared. And the question wants us to find the area to the left of 0.85 grams per centimeter squared. Now this corresponds to a z value of, which is and if we look up the probability corresponding to a z value of minus 1.5, we see that the probability is 0.0668. One thing to note here is that we should be referring to the one-tailed z values and not the two-tailed z values, because we only want to find the probability that this we have values which are less than 0.85. We don't want to find the probability that we have values greater than one standard deviation above the mean. In the previous question, we found the area of the curve to the left of 0.85. This question wants us to find the area to the right of 1.15. We could argue that because the normal distribution is symmetric, the area that we found in the previous question would be exactly the area that we would find in this question as well. But let us just go through the numbers to confirm that that is the case. In this case, the z value is and if we look up the probability distribution, we'll see that the p-value corresponding to this is 0.0668, which is exactly the same value that we found in the previous question as well. This question is a straightforward application of the binomial equation again. We have n equals 5. We are given that p is 0.513, and we want to find the probability of x being 4. And this, recalling the expression that we had for the binomial distribution, and if we do the math here, we'll find that the answer is 16.9%. So there is a 16.9% chance that out of the next 5 births, exactly 4 are boys. Question 6 has an approximately normal distribution with a mean of 80 and a standard deviation of 10. We need to find the value of x such that we have 25% of the normal distribution area to the right of x. So the first step here would be to find the z-score corresponding to 25% in the right tail. And we can look this up in our z tables, and we'll see that the z-score that we would be looking for is 0.674. Now it's a simple job of plugging this into the formula for z. We know that z is x minus mu by standard deviation. We can flip this around, make x the subject of the formula, and say that x is z times standard deviation plus mu. which comes out to be 86.74. Thus, to ensure an A in this class, we need to get a score of at least 86.74. This question has a doctor who performs 8 operations a day. The probability of success of any one operation is 95%. We want to find the probability that the doctor has exactly 2 failed operations on a particular day. Directly applying the binomial formula to this question, we have 0.95 raised to 6 because we have 6 successful operations, and 0.25 raised to 2 corresponding to the 2 failed operations, and we see that the probability is 5.1%. This question has the same doctor as in the previous question. He still performs 8 operations a day. The probability of success of any one operation is still 95%. Now we want to calculate the probability that a doctor has 2 or more failed operations on a given day. There are 2 ways of solving this question. We could either find the probability that the doctor has 2 or 3 or 4 or 5 or 6 or 7 or 8 failed operations on a given day, or we could just find the probability that the doctor has no failed operations or 1 failed operation on a day, add them up, subtract them from 1. That should give us the same answer that we're looking for. And because the second method actually has us adding up only 2 terms of the binomial distribution, it's actually much simpler to calculate than the first method here. So that's the one that we'll be using. The probability of having no failed operations on a given day is the probability of having 1 failed operation on a given day is and if we just add these 2 terms and subtract them out from 1, the answer we get is 5.7%. We can model this game using the following tree. We have 2 outcomes for this game. Either we win the game or we lose the game. If we win the game, we get a payoff of $1 million. And if we lose the game, we get a payoff of 0. But either way, we have to pay $50 to play the game. So the total payoff in case we win is $1 million minus 50. And the payoff if we lose is negative $50. Let's say the probability associated with winning is P and the probability associated with losing is 1 minus P. Let's find out what the value of P is. The probability of winning is the probability of getting either 3 or 4 sixes. Now we can model each of these 2 expressions using the binomial equation. In this case, the binomial is the fact that we have 4 die, n is 4, and the probability of getting a 6 on any one die is 1/6 because this is an unbiased die. So we get the probability of getting 3 sixes as by 6 to the 3rd and 5 by 6th. The probability of getting 4 sixes is this gives us the total probability of winning as 0.0162. Now we can use the value of P that we found, which was 0.0162, to find the expected value of this game. We know that P is 0.0162, 1 minus P is it's actually 0.9838. The expected value of this can be found using the expression that we have for the expected value of a discrete distribution, which is summation of x times P of x again. The payoff when we win is $1 million minus the 50 that we pay to play, and the probability of us winning is 0.0162, and the payoff if we lose is a negative $50 times the probability of us losing, which is 0.9838. And if we do the math, we'll see that the expected value for the game comes out to about $16,000, which tells us that the expected value is positive. Question 10 has a binomial distribution, but we are told that we can use a normal approximation. Before we go on to the normal approximation though, let's just find quickly the expected value and the standard deviation for the binomial distribution. The expected value is n times p. N in our case is 200 and p is 0.5, which gives us an expected value of 100. The standard deviation is n times p times 1 minus p, which comes out to 7.07. Let's now go to the normality approximation. We have a mean of 100 and a standard deviation of 7.07. We want to find the probability that a number chosen from this distribution turns out to be greater than 112, which is just equivalent to finding the area to the right of 112. Let's just find the z-score corresponding to 112 before we go on. We know that the value of z is given by x minus mu by standard deviation. This comes out to 1.7. And thus the probability of choosing a number from this distribution and finding that number to be greater than 112 is the same as having a probability of z being 1.7 or more, which comes out to 4.45%. In this question, we are considering a variable called wake up time, and we have 24 observations for this variable. We have the histogram, the normal probability plot, and the results of a formal test of normality, and we need to decide whether this variable is normally distributed. Now, the histogram is approximately normal, even though it isn't exactly normal. The normal probability plot is more or less a straight line, and the value of p that we get from the formal test of normality is 0.25, which is quite high. All three point to the fact that we can treat this variable as approximately normal, even though we know that it isn't exactly normal.